Okay, I'm going to continue on with ThreeJs here, the API for WebGL. Let me get the share screen going here. So there are a lot of things that we can do with ThreeJs. Area lights, advanced geometries, particles, grouping objects, merging meshes, various 3D file formats that are importable, and image effects and custom shaders. Today I'll talk about area lights and image effects and custom shaders. These kind of go together. So area lights are more advanced than the traditional direction, point, and spotlights. We haven't talked about how these are done. But they're done with a multi-pass shader, which is a complex things that we haven't talked about in the traditional line of things. There are a couple of different things that we have to add in order to be able to do this. With our simple stuff, we were using a WebGL renderer. But with area lights, we need to use the WebGL deferred renderer, as well as half a dozen different libraries that have to be included. We have to include the JS for the WebGL deferred renderer, shader deferred, render pass, the effect composer, the copy shader, the shader pass. I'm not sure if we need the FXAA shader, but I'm going to include them, and the mask pass. These are all things that are necessary for the area light, which I can show you over here. Here's the area light. These are panels that emit light. In this one, I can fiddle with the different colors here, the 3 different panels, and see the effect of it. All of these, area lights deal with post-processing. There's documentation here linked below for how to use this post-processing. Post-processing is going to be used for other effects such as blurring, depth of field, and various cinematic effects, as well as custom shaders, where we write the shader. It's been nice so far with ThreeJs that we haven't had to write any shaders, but at some point we want to be able to do that, to write shaders of our own. With the deferred renderer, the setup is a little different. We have some extra options. For instance, when we make a renderer that's a WebGL deferred renderer, we have the usual window height, width, and height. We have a scale with anti-aliasing turned on. I believe that's why we need the FXAA shader. I'm going to also include tone mapping, which is a filmic operator with a particular brightness that we set. Setting up area lights is similar to other lights, except we have the additional width and height of a light. And I also note that the area light is a horizontal plane, emitting light downwards, so it's kind of meant to be a ceiling light, but we can of course turn it sideways by rotating it. So area light 1 here is a new 3 area light. I'm using the FF000, which means it's going to be red, and I'm setting its initial intensity to be 3, setting its position and its rotation and its width and its height, and adding it to the scene area light 1. I do the same thing for the green and the blue panels at some point. The area lights emit light, so they would put light on the various different scenes, but we don't actually, of course, see the light. So to see the light, see the panel that emits the light, we have to provide a plane geometry to match that area light. We need a basic material for the light. We don't bother with Phong material since this is going to be emitting light. We set its RGB color of the to be the area light's intensity divided by 5. Area light intensities go greater than 1. And so we want our color scaled down, in this case by a factor of 5. I'm going to allow the area light's intensity to go up to 5. So area light intensity divided by 5 is going to max out at 1. I make a plane geometry and geometry material. I position it at the same place as the area light 1, and I add it to the panel. For some reason, the plane geometry scale is not the same as the area light's width and height, so I had to make it a little bigger to match the reflection that you see in the surface here in front of it, this kind of reflection. So in the sample, you noticed I was able to vary the intensity of the area light. And this, of course, in our controls requires a bit of fiddling. Our controls have intensity 1, 2, and 3 with their default value at 2. And this is our GUI that we're adding up here. The slider for each of these, we have an intensity 1, 2, and 3 for the 3 different colors. The slider goes from 0 to 5. It has an on-change function where the on-change function is going to catch that intensity. I'm going to change the area light's intensity, set the material of my plane to be that intensity divided by 5. I'll take out the plane that's there, make a new one, set it to be in the area light's position, and add it back to the plane. So as I change the intensity over here of one of these lights, in each case I'm disappearing and reappearing that plane with the appropriate intensity. So that's all very cool. It's an interesting light that it does, I believe, cast shadows and other things. It makes that nice shiny reflection. The plane, incidentally, here is a Phong material that has a specular component and so forth. You can look at the script to see that. The area lights uses this deferred shader, and all of the post-processing effects like bloom, blur, rendering your object as dots or simulating a TV screen, these are all post-processing effects. And there are also a number of predefined filters that allow for you to do a kind of Photoshop manipulation of textures. You can change hue, saturation, you can do color corrections, you can adjust brightness and contrast. These are all demonstrated in various samples that I'll give you. Let me show you one of them while we're here. The 5D kind of has them all together. Let me close area light. It's pretty expensive to run. This 5D Shader Pass Simple has a lot of different shader effects. Colorify, which we can then open here, and I can change the base color of sort of the whole thing. Brightness gives us a Photoshop-like tool where we can adjust the brightness and the contrast of our image. And I'll let you play with these different effects here. Sepia makes it into an old-fashioned photograph, color correction, RGB shift, a mirror option, vignettes, and hue and saturation. These are all possible effects that we can play with here. So how do we do this? With the predefined effects, we have to have this minimal set of JavaScripts that are added, some post-processing effects from the library, effect composer, mask pass, render pass, and shader pass. And from the shaders, a copy shader. And then for whatever specific effect we might want, a bloom pass or a convolution shader, we need to include them in the JavaScript as well. The image effect shaders that are demonstrated in the 5D or the mirror shader, hue saturation, vignette, color correction, RGB shift, brightness, colorify, and sepia. And these will have to appear in our JavaScript as we set up the different shader passes that we're going to make through here. And as I mentioned, these have to be included in the HTML to load them. So we specify the different passes appropriate for the different options. The first one's always a render pass that takes the scene and the camera. Here I'm making a bloom effect with a bloom pass with various options here. The first one is the strength. The higher it is, the brighter the bright areas, and the more they bleed into the different dark areas. The kernel size is kind of how many pixels over which this is all blended. So it smears the image by applying this to a sort of square of pixels around the central pixel. Sigma controls the sharpness. The higher the value, the more blurred the effect. And resolution defines the precision of the bloom effect that's created. These are our three passes: the render pass, the bloom pass, and the shader pass, which is a copy shader. The effect copy, which is our copy shader, is the one that actually does the rendering, and so we need to set its render to screen to be true. So we add these different effects into the effect composer. So somewhere here we've got a renderer that's a WebGL renderer. We have a composer that is an effect composer that takes that renderer. And then we add our different passes, starting always with a render pass, ending always with an effect copy, and then whatever passes that we're adding in here, whatever effect shaders we're adding in between those two. Another thing that we need to do is include in the render function a composer.renderer with a delta time if it's necessary, instead of what we had before, which was renderer.render the scene in camera. Delta comes from a clock get delta. So writing our own custom shaders. So that's how we set up these different shaders. If you look at the HTML for this, it has all of the different shaders established and the different passes, and some of them are enabled or not enabled. uh, uh, we can include all the passes, but they can be turned on or turned off by enabling them. So those are all default shaders. It's worth having a look at some of these shaders because they're all just JavaScripts, and we can look at how they've written their custom shaders when we write our own. So let's imagine a custom shader here. For example, let's consider converting RGB images to black and white. And this is done in 5E Shader Pass Custom. Let me get that going here. I'll close this one out. Close that one out. 5E Custom Shader. So this is our custom shader that we're going to be, whoops, don't want to do that. This is our custom shader where we have some little globe here. Whoops. We have a globe, and I'll turn on the grayscale. And now I can adjust how much power comes from the red channel, how much power comes from the green channel, and how much power comes from the blue channel. Let me turn off rotation here. So we're getting different black and white images depending how I balance the combination of the grayscale from the red, green, and blue channels of my shader. A standard set of weights would be that the gray is 0.2126 times the red channel, 0.7152 times the green channel, and 0.0722 times the blue channel. These three weights should add up to 1. So we're going to be establishing our gray color as some combination of the red, green, and blue. And by making different choices, we get different images that combine the red, green, and blue channels of my original image into a gray scale that has different, for instance, here's just the red channel, here's just the green channel, and here's just the blue channel. And we get very different looking grayscales depending what we pick. So how do we do this? I'm going to add another shader in here also at the same time, one that sets the number of bits that we use to represent the color. Fewer bits means fewer available colors. Here's my bit shader that I turn on. Right now I have 8 bits of color. If I turn that up, I don't see much difference because I'm using that many anyway. But as I turn it down, you can see as I get down to just 2 bits, now I have much fewer colors. And so my shading is quite different. If I turn grayscale off, my colors are also limited in the number of bits that I'm using to represent the colors. Let me turn that off. So I'm going to have 2 shaders. I'll have a shader pass for the custom grayscale shader, and I'll have a bit pass for the custom bit shader, adding these 2. Similar to the way we specified the predefined shaders, such as Bloom. Those were just JavaScript files of shaders too. The shader, I'll show you the shader in a little bit. I need to add my render pass that's from the scene in the camera and my effect copy that's from the copy shader. And I need to turn on that effect copy render to screen to be true. And now in the composer, I'm going to add in these two effects. We start with the render pass, then we do the shader pass for the grayscale, then we do the bit pass for the limited bits, and then we actually display it with the effect copy. Shaders that we write have to be included in an external JavaScript file, a 5e custom shader, which I include in the HTML, just like I included the bloom and other effect shaders with a effect shader. Now, in writing these custom shaders, I'm going to be passing them various uniforms that will be affected by our shader. And so in the JavaScript where we're doing the ThreeJs, I'm defining this custom grayscale shader to have uniforms, a T diffuse of type T, that means it's a texture, R, G, and B powers that are F type floats with initial values 2126, 7152, and 0722. So that establishes their initial R, G, and B powers. The JavaScript, this external file that we're writing, 5e custom shader JavaScript, is now going to connect to that shader. And it has two parts. It has a Vertex Shader and it has a Fragment Shader. The Vertex Shader with these custom shaders is always the same. The UV, position, projection matrix, and model view matrix are all handled automatically. We only have to include a varying for the UV texture, a vec2 VUV. And in the main, all we have to do is store our UV texture into that VUV. And do the usual GL position is projection matrix, model view matrix times our position. I believe the position is handled as a vec3, so we have to add the one onto it ourselves. Note the way this is included. We have Vertex Shader and then a set of a square bracket that closes here and here. And then each individual line of the shader, is enclosed in a pair of quotes, a quote here, a quote here, a quote here, and a quote here, and so forth. So we're including all these lines as strings, essentially. This Vertex Shader is an array of strings, each of which is a line of the shader. And then finally, we have to put the end of file on it with a \n. And this is just ordinary GLSL code like we have written before with our author's code, except of course it's presented in a different way. The fragment shader is where the work gets done for these custom shaders. And so here's where the uniforms show up. So my fragment shader, again, starts with a square bracket, and then individual lines for each of the different lines of our shader, enclosed in quotes. We have a uniform for R, G, and B power. We have a sampler for that texture, and we catch that varying vec2 VUV that came from the Vertex Shader. We have the main function, and of course you can write your own functions just like we did with regular GLSL, everything enclosed in these quotes. So I start the main here. I'm going to do the sampler from the diffuse texture here, at the VUV varying texture coordinate. And then I'm going to form the gray color, a float, as a combination of each of the texels from the texture, the red, green, and blue channels scaled by the red power, green power, and blue power. And then I'm going to assign to the fragment color a vec4 of that, the gray color. This is putting gray in all three slots of the vec3. And then I'm including the W texel of whatever that is there for transparency, for instance, and then ending it with a join and ending the whole shader with this extra curly bracket and semicolon. You can look at the shader when I distribute the code. The custom bit shader has uniforms. Again, we've got a type T for a texture, a bit size, type I for integer with a value 4. The Vertex shader is exactly the same, only the VUV varying gets passed on. Everything else is the same. And then in our fragment shader, I'm going to have my uniform integer bit size, my uniform diffuse texture sampler, my varying, and in the main I'm going to sample from the diffuse texture into texel. N is going to be a bit size raised to the power 2. This is going to be the number of bits that I want. And I'm doing a little integer arithmetic here where I get the new red, green, and blue channels now with a texel.r times n divided by n. So this is going to reduce the number of, this is going to reduce the number of bits, effective bits in my color shading, and then just add that all in with a 1 in the fourth slot. Some other details you might find interesting. This planet object that we're playing with over here, which you notice is not shiny over the land, but it has a specular highlight here over the ocean. Water is shiny, land is not. Is kind of an interesting one. So first of all, the planet, we created a sphere, radius 10, 40 steps in the latitude and longitude. And we're going to have 3 textures here. So with our, when we create the mesh, we're adding in to our planet 3 textures, an Earth texture, Earth PNG, a specular texture, Earth spec PNG, and a normal texture for bump mapping, Earth normal.png. These are all part of our create mesh geometry. The Earth texture is just a map, a Mercator map of the world, essentially, that's going to be mapped onto our sphere. The Earth specular is a mask that is white where we want, it's white where we want it to be shiny, to have a specular component, and it's 0 where we want it to not be specular. So land is all black, ocean is all white, and that's why we have a specular highlight over the ocean, but not over the land. It's not really turned up that much, but here's the Earth normal map. This is a bump map, like we talked about in class, that makes for topography. So there is a little sense of vertical relief in here. just so that you can see that it's actually there. I took that texture into Photoshop and equalized it to bring out what the texture is. The relief of the Earth, here's, mountains, mountain ranges, are all indicated here by texture mapping in the Earth normal, but it's not very strong. It's a subtle effect. So now that I have these three materials, I can make a mesh Phong material. Phong is the material that has shiny highlights. I can add to it a specular map. That's my specular texture. That's that black and white map of the world. I can assign a color to the specular reflection. Here, different, a little more in the red and the green, less in the blue. No, the other way around, more in the blue. A little red and green and more in the blue. I assign a normal map to the normal texture and to the map. This is the underlying texture. I give it the planet texture, and I can adjust the shininess. I think I left it at the default value. That appears to be turned off. So now that I have that material, I can create a multi-material object with the geometry that I specified for the sphere and this array of planet materials that were specified up here, the planet material. And I return the mesh, and I'm ready to go with that, and it all just works. You might be interested in how the GUI is set up, this GUI that allows us to adjust all these different things. I have a set of controls for the grayscale, Boolean that's either on or off, by default off, the default red, green, and blue powers, the bit shader that's by default off, and the rotation flag that I believe was by default on. So that's our controls with the default values. We have various different callbacks for the GUI. We have an update effect film function that takes from the grayscale whether the shader pass is enabled or not. We can turn on and off the different shaders. It gets from the controls red, green, and blue power. The shader pass uniforms red, green, and blue power values. So those are then assigned. The update bit function also sets whether the shader is enabled or not, and it also sets its uniform bit size value to be the control bit size, and the update rotation just gets the rotation flag, whether it's true or false. The GUI for the gray menu, these different sliders here, we're adding a folder so that now we have this folder for the grayscale. So we have kind of a subfolder. I'm adding controls for the grayscale. That's what shows here. On change, we'll call the update effect film function. For the red, green, and blue powers on change, we'll call the update effect film. These are sliders that go from 0 to 1. For the bit menu, which is another folder, we have these kind of folders that we can open and close for these. We have the bit shader on change controls. We're going to call the update bit function. And for the bit size, we're going to call the, we're also going to, on change, we're going to call the bit update bit. And for rotate menu, that last folder down here for the rotation, we're just going to, on change, we're going to update the rotation. Passes. So that's how this all works, and that's very cool. Now, another trick that we can do with this is, let me turn this off, we played with the trackball and we saw how easy the trackball was to operate in ThreeJs. But if we want to have some objects that are trackball orientable and some objects that are static, we have to be a little tricky with this. And we actually use shader passes to accomplish this effect. And the way we do it is to have two scenes that we're going to render and two cameras that we're going to take pictures with. And we're going to combine those two scenes and cameras with the composer. So here I'm going to have scene that's a new scene and scene 2 that's a new scene. I'm going to have the first camera that's a perspective camera, field of view of 45, aspect ratio near and far clipping plane, and I'm going to have an identical camera 2, also perspective, also same aspect ratio, also same near and far clipping plane. Each camera could be different. You could have one that's a perspective camera, another that's orthogonal. In this case, I actually want them to be exactly the same. And I'm also going to set them at exactly the same position with exactly the same thing that they're looking at. So they're both set at 20, 20, 20, and they're both looking at the cube. So they're identical. They're taking the same pictures of the scene. So we have this RGB cube that we want to control with the trackball. It's going to go in the first scene. And the reference plane that we don't want to move, we're going to put in the second scene. So we make our cube and add it to scene, and we make our plane and add it to scene 2. And the trackball control the camera that is associated with the scene that has the cube in it. We now set up the various passes. Pass 2 is going to do the static scene with camera 2 and the plane. And the render pass is going to do the RGB cube with the trackball controls, the scene and the camera. And we're going to combine these with effect copy that does the actual rendering. So when we set up our passes, we have pass 2 that is scene 2 with camera 2. We have the render pass that is scene and camera. One trick is that in render pass, we're not going to clear it. So we're going to leave it there after the pass. So that render pass is clear is false. And then the effect copy that we have to make to combine these passes into with, of course, the effect copy render to screen set to be true. So those are our 3 passes. And in the composer, we have to add these in the order that we want them to trigger. Pass 2, that's going to do the static scene, render pass, that's going to do the rotating cube, and the effect copy that's going to combine them and actually display it. As with other multi-pass effects in render, after the request anim frame, we have to use the composer renderer instead of the renderer render. And since we're using a trackball, we have to have that clock with the update delta that we use to update our trackball controls. And so that's, now we get this, the trackball moves, We can move our object around. We can zoom and pan on it. And this plane rendered with a separate pass of the renderer is appropriately static. So let me conclude the sharing here of the screen. So that's multi-pass shading, custom shading, area lights, all of which use this multi-pass shader, and the ability now to write our own shaders. It's a bit tricky. It does require some thinking outside the box to do, but it's all very cool. And there are lots of examples of shaders in ThreeJs that you can have a look at to see how they work. And I'm going to stop the lecture now, so I'll end recording and I'll see you in virtual class whenever that occurs. I think probably on Wednesday. So I'll stop recording now. Bye.